Different lectures today. The first part and the second part are basically not closely related. So let me just start the first lecture with this. This is a reminder from last time. Assume so S is a non-singular projective surface. Assume H1 of the structure sheaf OS is 0. And D is an effective divisor. And P in D is a singular point. So it's a point. It's either a singular point of one of the components, or it's a point of multiplicity multiplicity on D greater than or equal to 2. Right. And I want to assume that D is 2 connected. So I explained this at length last time, numerically 2 connected. Then it follows that P is not in the base locus of Ks plus D. Yes? So that's, this is sort of basically straightforward. This is, you know the rules of coherent cohomology, and you just play the standard game and you get out this result. Right? So I'll give this proof and it should be straightforward. However, we can also do it without assuming that. And this is much more substantial and much more subtle, and it involves the vanishing theorems. It involves understanding what vanishing theorems are. Okay, so let me first put this back in and explain that this is sort of rather easy thing. So the idea is this. I'm taking, the thing I really want is that MP, maximal ideal at P, times OS of D. I want that H1 of this is 0. Right? Because if I have this, then you know, there's a standard exact sequence, OS of D goes to OS of D, goes to the same, this is a line bundle. The line bundle restricted to a point is a one-dimensional vector space. You need to choose a basis here before you get a specific basis there, but it's a one-dimensional vector space, right? And then, I'm sorry. Ks plus D. Right, Ks plus D there. Okay, so if we can do this, if we can get out this H1 being nothing, then it follows that H0 here, the global sections, map to the global section. So this is just the sheaf supported at one point. Its global sections is just the field K, and that's surjective. And this means that the line bundle OS of Ks plus D has a section which is a local basis for this sheaf there. So there's a global section which generates the sheaf at that point. Right? So in terms of linear systems, it means that I can find an element in the linear system. I can find a curve C in Ks plus D so that P is not in C. Right? If you like linear systems. Right? So this is the aim. This is the aim of the assuming this is the aim. So you know, it's interesting. It'll be interesting to see later what happens. Anyway, as I explained last time, what we're going to do is S1 maps to S, the blow up of P. Right, and so there's an exceptional curve E. Then, so let me just give the idea of this calculation to say what this means. Then I can write down the canonical bundle KS1, the canonical sheaf of S1. And so I say that this is equal to F upper star of KS and then plus one copy of E. Okay, so let me explain what this means. So suppose that I'm standing at a point of S, so I'm at a point P there, and suppose I've got this X and Y local coordinates. So this means that X and Y are in OX of P, and they generate the maximal ideal. Right? We don't need X. The picture here looks as if I'm saying it. S is just affine space, but that's not necessary. The only thing I need is this very local algebraic statement. These two guys generate the maximal ideal. Right? So I can always do this. This is just the assumption that I have a non-singular surface. Right? And so the blow-up is a new surface, S1, here, and one affine piece of it looks like this. Right? So after I do the blow-up, this is the original x-axis given by x equals, sorry, let me say this is x equals 0, this is y equals 0. Right? So this is x equals 0 upstairs, and then this guy here is y over x equals 0. Right? So you know the S1 is contained in S cross P1, and it's the P1 with ratio x to y there. Okay, so you know if I ask who is KS, then there's a sheaf downstairs on S, OS of KS, and this contains the element dx wedge dy. It's a local basis. Right, and I lift this up to S1, and on S1, I have local coordinates x and y1, which is y over x. Right, so I take this guy here, dx wedge dy. So f upper star means, when I write f upper star here, it means I take the same functions. These are functions on S, and I consider them to be functions on S1 by means of this map F. Right? So dx by dy, well, this is the Jacobian determinant. So it's the determinant of the Jacobian of, d of x, y divided by d of x1, x, y1. Right, so the fact it's a canonical class times, I'm sorry, the Jacobian determinant, this is, all right, determinant, times dx wedge dy1. Right, and you figure this out, and this is a unit times y1. I hope I've got this right. So this E, S1 of minus E, is generated by x comma y. And near here, that means it's generated by this y1. And so what's the calculation I have to do? I write x equals x and y equals y1 x. Right, so now I do d by dx of this, and I get 1 y1, and d by dy y1 of this, and I get 0 and x. I'm sorry, so this is unit times x. Look, I don't care. Anyway, that's what this formula means. It means I take the thing which is the basis here, I lift it up there to give a differential on this new surface. So this is f upper star of dx wedge dy, and then I say, well, I can write it in terms of the dx. The x was a coordinate downstairs and is still a coordinate upstairs, whereas the y, it was a coordinate downstairs and now it's now a multiple x times y1. So this is unit times x. Right? X equals 0 is one of the local basis of this sheaf of ideals. Right? So x vanishes once on E, and that's this formula. Yeah? So at the same time, remember that I'm assuming that P is a singular point of D. So when I do f upper star of D, contains two copies of E. Right? The local equation of D at P must have multiplicity greater than or equal to 2 at P. So that means I take the local equation of D at P, I lift him upstairs, then he must vanish at least twice on E. Right, so I'm writing D double primed equals f upper star of D minus 2E. Right? And so remember, I mean, the thing I'm hunting is this cohomology group. I want to kill that cohomology group. Right? And so what do we have? Well, if I look at Ks plus D and take f upper star of this, right? And then I compare them with Ks1 plus D double primed. Right? The thing I want to say is that MP times OS of Ks plus D. Right? This is the same thing as OS1 of this Ks1 plus D double prime. Right, so what do I mean by the same thing? I mean it's the F lower star, or that's the other way around, that this one is OS1 of Ks plus D double primed is the image, okay, it's the image of, let me just leave it at that, that's fine. Okay, so if I take Ks plus D and I lift it up, then according to this formula, if I do f upper star of Ks plus D, I get Ks1 plus D double primed plus E. So I don't, that's not subtracting off both these copies. And so if I do MP times this K upper star, so take the inverse image of a sheaf of this guy, that's still that was a line bundle downstairs, so f upper star of him is well defined as a sheaf. Now I take MP times it, then I just kill this E. Right? So MP times f upper star Ks plus D is Ks1 plus D double prime. Right? And so it's enough to show that H1 of OS1 of Ks plus Ks1 plus D double prime is 0.
Maybe you meant at lower star of OS1.
Yes.
Ks1.
Yes, of course. Right? But but this is okay. We can prove this. Okay. So what do we do? Well, we're going to just use duality. So this is a line bundle here on the surface S, and so on a surface I'd have H1 of S and a divisor OS of A. This is H1 dual to dual to h1 of s and then os of ks minus a. Okay, so h1 is some complicated definition that we don't understand very well, and this h1 is also some complicated definition that we don't understand very well, so we don't seem to have won anything. Right? However, if I do this one, it's saying that h1, the guy I'm trying to kill, s1 of this ks1 plus d double prime, is equal to h1 of os1 of minus d double prime. Okay, and now we're in, now we can fit this into an exact sequence. So So now I'm going to look at OS1 and take sections of here and restrict them to OD double prime. Right, and so there's a sheaf. The sheaf of ideals here is OS1 of minus D double prime. Right, and so I do H naught here, maps to H naught there, maps on to H1 here. So this is the guy that we're trying to kill, and then this is going on to H1 of OS1. Right, and this one is 0 by assumption. So that's this assumption here, which I'm making at the moment. Right, and I showed last time that D2 connected implies that D double primed is 1 connected. So this is sort of simple calculation of intersection numbers, and this implies that H naught OD double primed is the constants and nothing else. Right, and so the sections of this guy are only the constants, the sections of this guy are only the constants. So when I do H naught, this is equality. Right, so there's no co-kernel, and then this maps onto there, and therefore H1 OS1 of minus D double primed is 0, and we've proved that P is not in the base locus of Ks plus D. Okay, so it's it's one of these arguments where there are sort of 3 or 4 steps. So you have to think, well, I'm trying to kill this H1 here of a sheaf which is not locally free. This is not a line bundle, and so let's blow it up to make it a line bundle. And then you have to think at some point we're going to use Serre duality to transform this H1 into another H1. So in general, this one here and this one here are, nothing is easier. Neither is easier than the other. But in this case, it so happens that we can control this guy. So this was this argument. I think it was probably around in the literature before then, but it's the one of the ideas in Bombieri. Okay, so this was what we aimed to do. This is what we were aiming to do. Okay, so how can we get rid of this condition? So I want to get rid of the condition H1 OS equals 0. I'm sorry?
Is the condition used only at the last time?
Well, I mean, it's so let me not immediately answer that question, but where have we used this? So I had this at the beginning. I had MP times OS of D plus K k plus d, goes to OS of k plus d, goes to the kp. Right, so we want to show that this is surjective on h naught. Right, and so I have h naught goes to h naught, goes on to h1, goes on to h naught. And then this goes to 0. I'm sorry, I'm confused. That's not what I meant to write down. So here I want to prove, I want h1 OS 1 of minus d double prime is 0. Okay, but if you think about this, this guy here, this argument here is only on D, right? And so this doesn't use h1 OS equals 0, right? This is perfectly clean, perfectly easy, simple argument, right? The where we used it is here, right? So instead of using it at the end of the argument to, in other words, in this very last step where I want to conclude that this h1 OS 1 of minus d prime is 0, and we could try to prove that h1 OS continues on into this exact sequence, continues on to h1 of OS O of d double prime. We could try to prove that this is injective, right? So injective here would also be good enough. Would also give the conclusion. Right, because it would prove that, so, you know, I mean, the thing that I've used here is that this is 0. Right? But if we happen to know that it includes into the next one, okay, then we're happy. Would also give the same conclusion. Right? Namely, I'd have, well, it's the same sequence here. I have h naught here is just the constant, h naught here is just the constant, maps onto mystery group, the group we don't know, and then it maps onto this h1 OS1. And if we know that this sequence is in the that this map in the sequence is injective, if for some reason or other we knew that this map is injective, then the kernel here is the kernel of this map is 0, so the image of this map is 0. Right? So this is what we're going to prove, or we're going to prove it under some circumstance, under some conditions. So now we get to the really clever part of Ramanujan's argument. So this is, I'm going to state it in two different ways. There's two slightly different results, but so Ramanujan's vanishing and there's also something called Francia vanishing, which I'm going to explain at the same time. So when I look at H1OS, maps to H1 of OD. So I'm really thinking S is S1 and D is D double prime on the surface. Right, so call this restriction to D, right? And I say that restriction to D does not really depend on D. So this is a strange. I'm sorry. The kernel of restriction of D does not really depend on D. So I'm saying this in a kind of paradoxical way, but what I'm more precisely, so if C twiddles maps to D reduced is the non-singular model, is the resolution of normalization. The non-singular model of the curve is the non-singular model of the curve D reduced. Right? So our problem is, the obvious way, the divisor I've been talking about, D double prime there, is possibly singular, possibly messy, possibly has many components of multiplicity, possibly its individual components are singular. So I say, well, let's just look at a much, much simpler thing. Let's take the reduced part of D, so just the support of D, right? And moreover, let's take the resolution of singularities. Then I can do two different maps. I can do the restriction map H1OS maps to restricts to H1OD, and I can also do H1OS restricts to H1 of OD reduced. So this thing is contained in there. So this sheaf maps surjectively to this one. Right? And I can also do H1 of OS. I can also do the composite of this with the resolution of singularities, H1 OC twiddles. Right? So, the picture is this. Here is D. Maybe it's got some multiple components like this. And so inside there, I see D reduced. Right? And then on top of that, I see C non-singular, C twiddles, the resolution of. So, in general, this might have many components and so on, in which case C twiddles means the disjoint union of the non-singular components. Yes? So this is resolution to, the restriction to D reduced, and this is restriction to C twiddles. Right? So it's not really a restriction map, it's restriction to there composed with this map to the, right? So Ramanujan says, Ramanujan and later Francia say the following very, very clever thing, that these maps have the same kernel. Right? So in other words, the kernel of restriction to D and equals the kernel of restriction to D reduced equals the kernel of restriction to C. Right? So these three maps, a priori different maps, have the same kernel. Right, so why is this good for us? So you know, in the case in the middle of the proof I was at before, I can, in practice, I can assume that the divisor d double primed is big. So in the previous, so assume this for the moment, and let's just continue the previous proof. So assume this, right? So this is subtle and difficult, and it only works in characteristic P, characteristic 0. So assume star, and then in the previous proof, assume also that d double primed is big. Right, so d double primed is big. I remind you this means that if I take some large multiple of d double primed, this moves in an arbitrarily large linear system. Right, and so in particular, eventually, for n, when n is large, this nd double primed minus h, some chosen very ample divisor, or even a chosen large multiple of a very ample divisor, is effective. Right, but this means that so the thing I'm saying, this if we assume that d primed is big, then some very, very large multiple of it is bigger than an ample divisor, or bigger than a large multiple of an ample divisor. Right, so if I was doing H1 OS and restricting to H1 OH, right, then the kernel here is H1 of O of S minus H. And by taking this very ample thing to be big enough, then this is 0 by Serre vanishing. Right, but at the same time, I can think of this as mapping to H1 of OS, of O n d double primed, right? And this is now, you know, what I'm saying is not completely honest, but so if I restrict to this divisor, restricting to this divisor has some kernel. Right. On the other hand, this is effective. So this is an effective divisor. So I can map this. Oh, I don't. Something like this anyway. So if I do H1 OS restricts to what do I want to say? Sorry, I haven't thought about this carefully. So this thing that I have here, I have the kernel H1 of OS of minus ND. Anyway, look, I'm sorry. Let me just leave it here. By taking a large multiple, I can assume that this map is. I mean, we know that this map is injective because this guy is 0, right? But on the other hand, this doesn't depend on it only depends on the numerical equivalence class of ND primed, and so also let me just skip one or two little steps here. I don't think there's anything difficult here. So therefore this one also maps injectively into H1 of O n d double prime. Right? But I told you the kernel of this map doesn't depend at all on who D is. It only depends on the geometric part obtained as the resolution of the irreducible components of D. So I apply this to this nd primed. Right? So the kernel of this map that we want is the same as the kernel of this map, which is injective. Right? And so this implies the that so if D, this implies this earlier statement. So if D double primed, if D is if D is 2 connected and D squared is greater than 4, then K plus D. Then and P is a singular point of D, then P is not in the base locus of Ks plus D. Yes? And in fact, there's a theorem, Francia has a slight improvement on this. Francia proves also that any S for any non-singular projective surface S in characteristic 0, any divisor D and a point P in effective, any if D is effective and P is in a singular point of D, then P is in the base locus of Ks plus D. And this is the good thing here. This is if and only if H naught of OD maps to H naught of OD double primed is surjective. Right. So this is a very strong result. This is basically the final result in all of this Bombieri. And this is an if and only if condition. Maybe I should give an example to sort of clear the air. So, what's the opposite of 2 connected? So, for example, if D is C1 plus C2, and C1 times C2 is 1, so this is, something like this, then P is certainly a base point of Ks plus D. So why? Well, you already know this. So if I take Ks plus D, I can restrict this down to C1, for example. Right? And what is this? So this is Ks plus C1 plus C2, restricted to C1. Right? And so what's this? This guy here by the adjunction formula is Kc1, and this is P. Right? And so when you do Riemann-Roch, I mean, this is the basic basic points, one of the basic points in the proof of Riemann-Roch is that if you look at a curve C1, non-singular curve, and I look at H naught, I look at the Riemann-Roch space L of KC1 plus the point P, then this is equal to L of KC1. In other words, you take the canonical class and then you add on one point and you say, I have differential forms with a single pole at P. And if they have a single pole at P, then the Cauchy residue theorem says you integrate around the pole and you get a residue, and that residue must be 0, and therefore it doesn't have a pole. Right? So this is Cauchy residue. Right? And so all of this messing around with two connected divisors and so on is a matter of, well, we want to talk about divisors on the surface which possibly have multiple components, so we can't use this very simple kind of argument. Right? Anyway, this argument of Francia says that this condition here, so, you know, here I'm doing this point and I'm by blowing up the point and subtracting off two copies of the exceptional curve, I'm doing the same thing as disconnecting the curve. So when you disconnect the curve, of course, this group is now bigger than it was before, right? And so it's you get the same conclusion from this argument as you get from this simple geometric consideration, right? But this also applies in the case where, you know, maybe like in the picture I had here, I have some really sort of complicated non-separation, non-reduced curve here, and I'm talking about making some modification at this point, maybe not a resolution, and then I'm doing this d double prime thing. Okay, so I'm not going to give the. I mean, the proof of this is just you know, the same ideas that I'm talking about here, but you have to argue it a little bit more patiently than I've got time to do. Okay, so let me describe. So the thing I've lectured so far today is, so if you believe this thing, then we have this this statement that will, in particular, for if I do r k x s squared is greater than, I think, 3 or something, r plus 1 ks is, let me just say 5 there to be safe, but I think 3 was probably enough. Then r plus ks is free linear system. Of course, in my case, S was a non-singular projective non-singular surface and is a minimal model, and Ks is an F and B. Right. So this is sort of the first half of Bombieri's theorem. Okay, but I have to explain why this is true. And so, you know, this is sort of now we're in a different world. So the arguments I've given here are all to do with coherent cohomology. So now we're in the world of vanishing more generally. Hello?
What do you mean by I times ks is
Squared. So you know, I told you last time we have these criteria for when you know different conclusions when this is 5k or 4k or 3k, and they usually depend on k squared or, you know, some silly thing. Right. So I'm you know, I'm going to talk about two quite different proofs, quite different strategies to prove Bombieri's theorem in the next few lectures. So I'm not at the moment trying to give the definitive results. I'm just trying to give the methods. Okay, so we ask the question, this is a philosophical question, who is H1OS? So it's a coherent cohomology group, but if you say, well, you know, I'm only going to work in coherent cohomology, then you're not going to make progress. And so we're going to relate this to topology, the Betti cohomologies, so H1, H2 of SZ. So this is the classical, in the classical topology. Over C. And then to...
There is something I don't understand. You say that Hilbert's point of this, if I don't leave this map is subjective. But in this example, the first group is C, and the second one is
two
C
copies
square.
of C. Yes.
How can be this map subjective?
Yes.
No.
Yes.
P is
It can't be. It can't be. And so P is always...
No, I don't understand.
I'm sorry.
Okay. Okay.
I'm very sorry.
No, no.
The person at the blackboard is always blind. Right. So here we, you know, arranging for this guy to have no things was the key to proving that P is not in the base locus. Yeah. Yeah. Thank you. Thank you. You should have said it earlier. And eventually to the pick 0 of S, which is an abelian variety. So, you know, this is a strange thing that, you know, we want to do things in coherent cohomology, but these vanishing theorems are outside algebraic geometry. They're not really coherent cohomology. Right? They depend on topology. So let me write down this statement, this which is in modern form due to Janos Kolar. So this is a slogan, Kolar. So vanishing is when a coherent cohomology group is controlled by topological cohomology group. Okay, so I'm not going to try to explain the slogan in its full glory, you know, which is a long thing. So, you know, most of the people in the room are young and will have a lot more experience of algebraic geometry in the future and will eventually come to understand what it means. It's it's a slogan. So what can we do with H1OS? So H1OS, well, you know, it's this coherent cohomology group. But in analytic topology, there is an exponential sequence. Right, and so it goes like this. Here's OS. I take. So this is always analytic. From now on, OS means OS analytic. We're over the complex numbers, and I'm talking about the complex topology and the sheaf of analytic functions. Right, so I can, if I've got an analytic function defined locally near a point, I can take its exponential. Right, and that maps to a function which is not 0. Right, it's a homomorphism from functions on S with addition mapping into functions on S under multiplication, and they're non-zero functions. The exponential of a exp of z has no 0. Yeah, and what's the kernel? Well, the kernel is the guy whose exponential is the identity, and that is z mapped in by multiplication by 2 pi I. Right, so if I do H1OS here, well, you know, it receives H1 of S with coefficients in Z. In fact, this is injective, right? And this goes on to H1 OS multiplicative, and then this goes on to H2. Okay, so this guy here is, I mean, of course it's analytic, not algebraic geometric, but it is the Picard group of S. Right? It's the group of line bundles on S. So, you know, if I've got a line bundle L, then if I restrict it to small open sets, L restricted to U is O. That's what it means to be a line bundle. And L restricted to V is also O. And then, you know, what I have to do, the fact it's a line bundle means that I can identify them here. Identify here. And this is by an element, a transition function in H1 of OS multiplicative, the automorphisms of O are O star, right? And this is, sorry, over the open set U intersect V. OS multiplicative, right? And so these transition functions form a one co-cycle, right? And so I get this group there, right? So then it maps onto this. So I'm going to write pick naught of S is the connected component. Right. So by construction, these are the guys there that map to 0 here. So this map here is the second Chern class. It's taking a line. I'm sorry, the first Chern class. It's taking a line bundle into its class in cohomology, into its first Chern class. Right. So I'm taking, and the first Chern class. This includes torsion. This group may have torsion if pick has. If the group of connected components has torsion, then that'll be reflected in this first Chern class, right? This H1 of OC is a vector space. It's a vector space over the complexes, so it's in particular it's connected, right? So that's mapping there to the connected piece. Yeah. So now, so S is a non-singular algebraic surface in characteristic 0, and so it follows that. So it is known that, this is Hodge theory and so on, I don't really want to go into it, H1 of OC of OS is this vector space C to the dimension Q. Q is the irregularity. Right? And H1 of SZ, this is the topological first Betti number, this is Z to the 2Q. And the inclusion map of the one into the other, Z 2Q into CQ, is a lattice. So in other words, it's a discrete co-compact subgroup. So it looks like, it really looks like Z to the 2Q contained in R to the 2Q. So these 2Q vectors, if I choose a basis of this, then they map into elements in this Q-dimensional complex vector space that are linearly independent over R. Right, so it looks like this. Right? And this means, so lattice means discrete and co-compact. Right, so it really looks like, here's the space, it really looks like this. If I take a basis here and I translate by this basis, then in this vector space C, I get some compact fundamental domain for the action. Right? And this means that CQ divided by ZQ is a complex torus. Right, so topologically it looks like S1, the ordinary circle, to the power of 2Q. If Q is 1, then this is 2 copies of Z included in complex numbers, looks exactly like this, and this is the standard construction of an elliptic curve, uniformized. Okay? So, we're going out of the coherent algebraic geometry, and we're doing it for a reason. So, if you think about this covering map here, I'm sure lots of you have done a course lots of you have done a course in differential geometry or Lie groups. So this thing here is a Lie group. It's usually this complex torus there, right? And this map here, the exponential map from a vector space onto this map is called so if I think of this so this guy is an analytic group. It's a complex torus. And this guy is his universal covering, but you can also think of this as being the tangent space at the origin to this space, and this map here as being the exponential map in the sense of algebraic groups. It's the map from the Lie algebra to the group. Sorry?
Zero is a complex torus. Peak is not.
Oh yes, okay. Pick 0. The connected component.
Yeah.
Connected component of the origin is this complex torus. So the punchline is that the Jacobian of the curve C is also a complex torus, and I can restrict from one. If I want to take the tangent space to this map. So when I'm looking at this map here, I've got something which is a tangent space to an abelian variety, mapping to the tangent space to another abelian variety, and that's very, very good. We don't know what that can be any kind of morphism we like. However, the kernels in here cannot contain any abelian group. It cannot contain any abelian variety, right? So I'm going to say this more generally, but I'm telling you the punchline. I'm telling you how the argument's going to finish. So the kernel of these maps cannot contain any complex toruses. Right? So that's the punchline. This is a subtle argument that's you're not going to understand it immediately on reading. So here, when I've gone through, S is a non-singular projective variety. Likewise, C twiddles, non-singular projective variety. And so when I look at their H1, I can say that their H1 is the tangent space to an abelian variety. Right? And so I have a map here which I don't know too much about. Right? So the map has some kernel and I don't control it too much. However, when I start in this non-reduced part, then this H1 is possibly a bigger group, possibly the kernel of this map, possibly this kernel here it could be a big vector space, right? But it cannot be the tangent space to an abelian variety, right? Because we can describe the kernels in coherent groups, right? So I hope I'm not making this unnecessarily complicated, but it is a simple story. Okay, so if you think about mapping OD to OD reduced, I can write H1 of OD multiplicative here and H1 of OD multiplicative. Right? And these can still be made into algebraic groups. So let me instead of so for example, e.g. if D is 2C, C non-singular curve. Right, then I can be interested in what is H1OD to H1OC. And I can also be interested in what is H1OD multiplicative to H1OC multiplicative. Yes? And so the kernel of this, the kerr is H1OD OC of minus C. Right, and this is what it should be, because this is coherent group. This is a coherent group, and all of this sequence just takes place in coherent cohomology. Okay, but now what about the kernel? What about the kernel here? What's the kernel? Can you see the points? So the point is that the kernel here is equal to H1 OC of minus C. These two kernels are the same thing, right? So what's happening here? What's happening here? So this group here is not a coherent cohomology group. right? I mean, it doesn't matter. This isn't a matter whether we're in the Zariski topology or the analytic topology. This group here, this sheaf here, multiplicative sheaf, is certainly not a coherent OS module. So there's no reason at all why this, why either of these groups, these groups. Right. On the other hand, if you look at the kernel here, so it means I take a function on 2C. So I take this function on OT2C, and I take functions there that map OC. So I take the kernel of this. Right? This has an exponential map. Right? So it looks like, so the functions that I'm talking about here look like a function plus x times another function. So let's have f0 plus f1, right? Where x equals 0 is the equation of C, right? And so I claim that I can write down exponential of f0 plus xf1. Right, so what is it? So it's exponential of, the f0, I'm working on the kernel, so the f0 is 0. So where the f0 is 0. Right, so the exponential of xf1 looks like, well, it's xf1 plus, hey, x squared f1 squared over 2. Hey, this is good because x squared is 0. Yes? So, I'm working with these guys which are nilpotent of order 1, and therefore if I look at the kernel under multiplication is also a group under addition. Right. Okay, so I'm just rubbing out the thing that I'm trying to prove. So let me just sort of try and state the. In the second half of the lecture, I want to talk about. In the second lecture, I want to talk about something else. So I want to let me just finish this with a statement, and you can believe it or not. So H1 of OD. H1 of OD is the tangent space at the origin to the multiplicative group H1 OD multiplicative. Right? So this is the moduli space of line bundles on D, or whatever you like. Right? But it has the structure of an algebraic group. So this is an algebraic group. Now if I do H1 of OD multiplicative to H1 of OD reduced multiplicative, so this is a homomorphism of algebraic groups. Right, and so the H1, the map from H1 to H1 is just the map between the tangent space and H1 OD to H1 OD reduced is just the induced map on the tangent space. But the point is that the kernel here, this is a homomorphism of algebraic groups, so it has a certain kernel. The kernel, I say, is an extension of multiplicative groups and additive groups. So there cannot be any abelian variety in there. The kernel of H1 OD multiplicative to H1 OD reduced multiplicative and H1 OB multiplicative reduced to H1 OC twiddles multiplicative. So these are, all of this is algebraic groups. These are nice maps between nice homomorphisms of algebraic groups, are extensions of GA and GM, and can't contain any abelian variety. Okay, so you know, I mean, you can understand this in principle, even if some of the words are difficult. I mean, this is a difficult this is a non-trivial subject. So I'll take it up again maybe in a week's time and try and make it a little bit more convincing, because I think we don't need it in this at this level of generality in any case. But so you know, logically, I've got this H1OS maps to H1OD, and then maps to H1OD reduced, and then maps to H1OC twiddles, a resolved reduced part. Right, so I have these maps, these morphisms. So these morphisms are homomorphisms, are tangent spaces, the individual vector spaces are tangent spaces to algebraic groups. The individual morphisms are induced by homomorphisms of algebraic groups. This guy here is purely abelian variety, purely complex torus. So actually it's an abelian variety for reasons I haven't told you. Right? On the other hand, when I do so H1 OS multiplicative is purely complex torus. Here also H1 OC twiddles multiplicative is also complex torus. I'm sorry, connected component. And the same here. Right? On the other hand, when I do homomorphisms, when I do the homomorphisms down here, then the kernel of these maps are things that can be described in coherent cohomology. Here, when I'm passing to a reduced variety, the kernel here is this succession of extensions. Right? So let me just give an illustration of what happens here. So you know, if I do this, I'm sure people have seen this picture. I've got a curve C with a node. And here I've got C twiddles its resolution. Right? So this C has a perfectly good H1 OC multiplicative, and the connected, this is an algebraic group, so the connected component is an algebraic group. Right, and likewise here. So here I have H1 OC twiddles. This is a projective non-singular algebraic variety, algebraic curve, and so this is connected component is the Jacobian of C twiddles. It's the pick 0 of C twiddles. Right, so what happens? What's the kernel of the maps from there to there? The kernel of F upper star is C star, C multiplicative. Right. So this case, this is the most basic surface curve singularity there is. There are two branches. When I resolve, I pull apart the two branches. So this vector space, this group here, parametrizes line bundles. So what's the difference between having a line bundle here and having a line bundle here? Well, the difference is there are 2 points here that get identified, and here I have one fibre over the origin, whereas here I have 2 different fibres over the origin. So if I want to make a line bundle here, if I want to make a line bundle here by gluing a line bundle here, I have to say, right, I'm going to choose a gluing of the 2 fibres over the origin. Right? And when I do F upper star, that's exactly what I lose. And this choice of a gluing is this F upper star. So, you know, maybe this is just one example, and I should spend a bit more time saying this more precisely. But, you know, this is, you know, anyway, this is how the Francia vanishing works here. You know, all of these things. First of all, they're coherent groups. If I restrict myself, if I close my eyes and say I'm only going to work in coherent cohomology, then we're not going to be able to prove these theorems. So we want to have this vanishing. We want to say these are coherent cohomology groups, and they have a topological interpretation, so that I can use this slogan of Collard's. So, you know, the argument is, maybe I'm not saying it completely coherently, and maybe I'll be able to say it slightly better next time. The argument is that these homomorphisms are the tangent spaces to homomorphisms between algebraic groups. And in those homomorphisms between algebraic groups, on this side here, because I'm working here, I'm taking a singular variety and making it less singular, then of course there can be kernels. However, the kernels are exclusively extensions of additive groups and multiplicative groups. Right? So these certainly both happen. Additive groups and multiplicative groups certainly happen, but never abelian varieties. Right? And this guy here is the tangent space to an abelian variety. And so, you know, he just can't, he doesn't have any chance at all of mapping in a non-trivial way to the kernels of these maps. And so therefore the kernel of this map and the kernel of this map and the kernel of this map are the same. Okay, so I'm sorry I made this a little bit complicated. Let's have I'm sorry. Let's start again at 6 o'clock. Sorry, start again at 5 o'clock.